Alright, so in this video, we're going to talk about how to implement the in-place heap sort. So in-place heap sort will, just use very similar idea to the heap sort using a min heap. So we can start with that function and just kind of convert the code uh, to do the in-place heap sort. Now, we one approach we can take is just modify everything at once and then hope that they just kind of work together. Well, the chance of success with that is probably isn't very high, especially the first time, and we'll have to perhaps spend quite a bit of time try to debug it and make everything work. Or a different approach we can take is we take several kind of intermediate steps, right? And at every step we have a particular goal, and that kind of moves us toward the ultimate goal of implementing the heap sort in place. And at every step we test it to make sure that things work. Then this is the approach that I'm going to show you. But even with this approach, it took me a little bit of time to get everything right. And as usual, if you have the time and you really want to practice your coding skills, then I encourage you to try to write the in-place heap sort on your own first. So my first intermediate step is basically just to identify what all the relevant code from the min heap, and then move them over into a kind of a single heap sort function with a couple of the helper functions that we need, and but just keep everything else kind of the way they were, other than to make this run and so that we can test it. Now, so a couple of the things that if you look at the heap sort min does, I mean, the first thing it does is to construct a min heap from the input. So that basically just involves doing the order heap operation. Okay, and then the second thing it does is it's doing the remove or extract min. And if you remember, the remove is basically a few lines of code, but most of the work that it does is the percolate down. So that's what I moved over, the percolate down operation. And the percolate down itself kind of needs the get min child index. So that's also what I moved over. Now, these two methods, they used to, because they are part of the min heap class, they used to use the self parameter, but now we work with the heap directly. So instead of self, we use heap. And then if you look at the main body of the heap sort is basically, we still put a none in front of the iterable. This is basically what order heap does. And then we clear out the input and we still do what the remove does, that we take the first item, well, the item or the element at index 1 and put it in the input, and then we move the last element up to the first element, and then we do the percolate down. So this is remove, this is order heap. And then now if you look at what the changes we have to make to percolate down, percolate down used to work on the entire input, right? But now, because we said over time the heap is going to shrink, so we don't necessarily always work on the entire input, so we have to know where to end. So that's why we have an extra parameter to percolate down end index, and instead of going all the way to the length of the iterable, we end at the end index. And then also the same story in get min child index. We don't always look all the way to the end of the input. There's a definite there's a definite end to where we should not look beyond, and that's where this end index parameter to get min child index is for. And now that we have a kind of an intermediate heap sort functional as usual, I always test it. So but the good thing is, to test this is really simple. So I just did this, and then I make sure it passed all the tests. So we know that even though we are not quite meeting all of our requirements yet, but at least we are getting closer to it. With our first step done, let's move on to the second step. And the second step does the two major changes that we discussed earlier. And the first thing is it does all the work in place of the input, the iterable, right? So as you kind of see, I no longer have prepend a none in front of the input. And the second thing is because of that change, then we have to modify how the child indices are calculated. And if you look at the main body of what the heap sort, in-place heap sort does, one of the changes we have to make is we used to the heapify process, the order heap used to go to just 0, and because the end index for range is exclusive, so it really doesn't go to 0. It ends at 1, right? But but now that we don't have something in the front, we have to go all the way to 0, and that's why this end index here becomes -1. Okay, and then the second change that we have to make here is the extract min operation, and also putting the min at the end. If you remember correctly, that's basically just the swap between the first element and the last element of the heap. So this is the swap operation. And lastly, the percolate down, again, we're not percolate down starting at position 1, right? We percolate down starting at position 0, and then at the end of it we have to do the reverse because it's sorted in the descending order. Moving on, let's see if we have to make any changes to helper nested functions. So for percolate down, there's really nothing to change. We already have the start and end index. The only thing we do is to just rename the parameter to the iterable to kind of signify it's the same as the input. Although you should know that this iterable, it kind of shadows the outer iterable, even though they are referring to the same thing, just the way that we're using it. Anyway, so for get min child, obviously we have to change how the left child is calculated. Instead of just the parent index multiplied by 2, we have to now add 1 to it. We don't have to change the right child just because it's calculated from the left child index. So that's really all the changes we have to make as the second step. And as usual, we always test it. We test the second step as well. So I have an intermediate step 2 test case, and if we run it, you should expect that it kind of pass all the tests. And with the second step, we are really very close to a final form of the in-place heap sort. The only thing that we want to do, we don't have to, we want to do is, remember there's a last step of doing the reverse. Here, reverse. We kind of want to save the trouble of doing that. So instead of using a min heap, we use a max heap. So I removed the reverse, and what we have to do for the max heap, remember we flip all the data comparison. So we basically just flip this, and we rename the helper function as well. Instead of get min child, we do a get max child, and then again in the get max child itself, we flip the comparison operation, and that's it, and that's the final heap sort, which I wrote, and it's called heap sort, just simple and straightforward. And if we run the test case, it's all good. And now that we have the in-place heap sort implemented, it would be kind of interesting to see how its performance compared to our original heap sort that used an explicit min heap. And here is the performance number that I have on my machine. And as you can kind of see, the in-place heap sort is almost it's 3 times faster than the heap sort using an explicit min heap. So as you can kind of see, the overhead of using the min heap, both in terms of the memory usage, we know it uses more memory, as well as the speed is quite significant. So it's a good idea to actually do the in-place heap sort. And then obviously once we implement the heap sort, we're kind of curious to how its performance compared to other sorts such as shell sorts or merge sort. And if you look at least the numbers that I obtained on my laptop, it's kind of in between shell sort, so it's quite a bit faster than the shell sort. But remember, the shell sort we're using shell gaps, which is not the best gaps. Anyway, it's heap sort is faster than shell sort, but it's slightly slower than merge sort. So anyway, that's kind of show you where it is with the heap sort in terms of its performance.